Welcome to this session on scaling through distributed training. First off, I just want to say that I really appreciate you taking the time to watch this session. My name is Sarah van der Moosdijk, but most people call me Moose. I'm a machine learning specialist, partner solutions architect at AWS based in Australia. So you probably want to know what you can learn from this session today. Distributed training has always been possible in Amazon SageMaker, but in this session, we'll take a look specifically at the new SageMaker distributed training library released for PyTorch and TensorFlow at reInvent in 2020. Please note that this is a level 400 technical session. This means you should already be comfortable with neural networks and training models on SageMaker. Preferably, you have experience building models in either TensorFlow or PyTorch. Now, we'll start the session by looking at why we need distributed training, after which I will provide a brief refresher on neural networks so we're all on the same page. Then we get to the core of the session, starting with data parallelism, followed by model parallelism. In the conclusion, I'll show you some results achieved with this library. So let's get started by looking at the history of neural networks and why we need distributed training more and more often. So in the past 10 years, the data sets available to us for training deep learning models have grown significantly. Probably one of the most famous data sets available to us, ImageNet, has grown from 3 million images in 2009 to 14 million images in 2020, with an increase in the number of categories from 5,000 to 21,000. In the world of natural language processing, the Stanford question answering dataset already had more than 100,000 question-answer pairs in version 1.1. It was then expanded to include more than 50,000 unanswerable questions in version 2. And these are all benchmark datasets, so you can only imagine how much more data is being produced on a daily basis by companies interacting with customers. Acting on this data has become an important differentiator for businesses in the past 7 years. This growing availability of data, along with the growth and power of our computing instances, has allowed us to build increasingly large neural networks. This graph shows the increase in the number of parameters for different language models released between 2018 and 2020. Note that the y-axis is in logarithmic scale. So if we look at one of the first models released in 2018, Elmo, you can barely see it on the graph with its 93.6 million parameters. On the other side of the scale, we have GPT-3, which was released in 2020 and has a whopping 175 billion parameters. To train these enormous models, we obviously need powerful computing instances. So to close off this section, let's take a look at how our computing chips have evolved. The most common and widely used computing chip is the CPU. These chips are a key component of any computing system because they can handle a wide variety of computations. A CPU is suitable for sequential processing because it usually has one core, or these days sometimes a few cores. To this day, a lot of machine learning can still be done on CPUs, but for large models and datasets, you really want something more powerful. Enter the GPU. GPUs were originally designed for rendering 3D graphics, but as they became more flexible, researchers took advantage of their parallel processing capabilities to perform a large number of deep learning computations at the same time. A GPU has more cores than a CPU, which is what makes the parallel processing possible. But these cores are more limited in the types of computations they can perform. So a CPU is still better for broad computational needs, but a GPU can really help you speed up for specific types of heavy computation. Another type of chip is the ASIC or FPGA chip. An ASIC chip is a highly customized chip which only supports very specific computations, but can perform these computations with incredible speed and efficiency. An FPGA is similar, but can be customized by a user who knows hardware acceleration programming. Both chips support a high degree of parallel processing. When you hear about companies releasing chips designed specifically for deep learning, then this usually means that it's an ASIC chip. Examples include Amazon Inferentia for inference and Amazon Trainium for training. Amazon also provides the F1 family of EC2 instances, which are FPGA accelerated. Although we have some very powerful instances available to us these days, some of those neural networks and datasets I introduced earlier are still too large to be processed by just one chip. So we need distributed computing to take advantage of a whole group or a cluster of these instances. Now, before I dive into the technical details of distributed training, I want to quickly refresh our memory on neural network architecture. This is just to make sure that we're all on the same page and we know what terms we'll be using moving forward. This session will be available on demand at a later date, so if you're not completely comfortable with neural networks, I recommend taking your time to read up on the topic before watching this session. Here's a basic, fully connected neural network with an input layer, 2 hidden layers, and an output layer. On the left, we have a data record with a number of features, and on the right, we have 3 output options. I'm going to assume that you know how data travels through the network with weights and biases. It is important for you to understand the forward pass and the backward pass with gradient descent, because this will come up later in this session. In the forward pass, your network will have specific values set for its parameters, and you pass your data record through this network to see which output node gets the highest score. You calculate the difference between your desired output and the output provided by the network, which is called the loss. Using the loss, you calculate the gradient, which represents how much you need to adjust the parameters in the network during the backward pass to hopefully get closer to your desired result next time. So now that we're all on the same page, we can start talking about distributed training, starting with data parallelism. Now, as the name suggests, data parallelism is a technique used when your data set is very large. On the left, you see my data set consisting of many data records. We could have thousands or even millions of data records. Now imagine we tried to train our neural network on a CPU. Since the CPU supports sequential processing, we can send it one data record at a time to run through the network. Running through the whole data set like this will take a long time. So what about a GPU? Well, this is already slightly better. Instead of sending one data record at a time, a GPU can process a batch of data using its parallel processing capabilities. So this would speed up our training process. So if one GPU is an improvement, then multiple GPUs must be even better. And this is what we call data parallelism, and this is where the SageMaker library comes into play. The library takes the data batch and splits the data between the GPUs. When each GPU has finished processing its batch of data, they then need to communicate their results with each other, so you still end up with a final neural network which has been trained on all of your data. Now, before we look at this new library in more detail, there are a few more techniques you should be aware of if you want to speed up the training of your neural network. These are methods which you can use independently of or together with data parallelism, and they all address another potential bottleneck, which is the time it takes to copy your training data from an S3 bucket onto the instance doing the training. Storing data on Amazon Elastic File System or Amazon FSx for Lustre and having the SageMaker training instance fetch the training data from there will speed up your training due to the performance and throughput benefits they provide. You can also store your data on Amazon S3, but use pipe mode to stream your data to the SageMaker training job. The advantage of this is that the job can start sooner, finish faster, and requires less disk space. However, it does require that your data is stored in the protobuf record I/O format. So if you're struggling with slow training jobs, just remember to try these options as well and not to rely solely on data parallelism. Now, let's take a closer look at data parallelism and how it works on SageMaker. Imagine we start up a SageMaker training job using 2 P3 8x large instance types, which have 4 GPUs each. We place a copy of the neural network on each GPU. These instances also have many CPUs, but to keep it simple, I have only depicted one CPU on each diagram. At the bottom, you see we have a dataset consisting of multiple data records. Now, I'm showing 2 P3 8x large instances because I would run out of room on the slide if I tried to show the larger instance types. But just remember to scale up before you scale out. If you need more than 4 GPUs, you should always start by choosing a larger instance type because there's less communication overhead between GPUs on the same instance. For example, the P3 16x large instance has 8 GPUs. When you've reached the maximum instance size and you still want more GPUs, then you should consider adding another instance. Since we have 8 GPUs, we can draw 8 batches from the dataset and send one batch to each GPU for processing. The main challenge is that all of these GPUs need to communicate their results with each other in order to take full advantage of training on the entire dataset. The good news is that you don't have to worry about this if you're using the new SageMaker distributed training library. It takes care of all this logic for you. But for curiosity's sake, let's take a quick look at how the library handles the communication between nodes. When you read the documentation on the SageMaker distributed training library, it states that the library uses a parameter server framework with balanced fusion buffers and a custom version of AllReduce. I'll try to reduce this down to a high-level explanation here. We still have our 2 P3 8x large instances with 4 GPUs each, which are called the workers in the parameter server framework. When a worker needs to process a batch of data, it receives the latest neural network parameters from the parameter servers. After completing its computations, it sends the gradients back to the parameter servers, which will be used together with gradients from other workers to compute the new parameter values. By having a shared parameter state, we ensure that each copy of the neural network on the nodes in the cluster is the same. The parameter servers are often the CPU nodes in the cluster. The balanced fusion buffers mentioned in the documentation are used to prevent the parameter servers from becoming a bottleneck. Some GPU workers might be faster or slower at finishing their computations, so instead of sending each gradient back to the parameter servers as soon as it has been computed, the workers will buffer a certain number of gradients, holding them until a threshold is reached. When the gradients are released by the workers, they can be evenly distributed over the parameter servers and immediately processed. The final component of the system is allReduce. This is the method used to compute the mean of the gradients coming from different workers. So let's take a look at how this works. There are different variations of allReduce, and the SageMaker library uses a custom implementation which takes advantage of the underlying AWS EC2 topology to be as efficient as possible on our infrastructure. But to keep things simple, let's take a look at a generic version of allReduce. Imagine you have two parameter server nodes, and each node has received specific gradients from specific workers. The goal is to calculate the mean of the gradients, where you need to combine A1 with B1 and A2 with B2. Each parameter server takes on the job of computing one of these gradients. It receives the matching gradient from the other parameter servers and passes gradients which they need as well. Then, the correct gradients are averaged out to form the combined gradients S1 and S2. Each parameter server now has one gradient, S, and shares this value with the other parameter servers, so the whole system has the same state. Again, this is a simplified explanation of how this works, and I recommend reading up on it if you do want more detail. Now, hopefully you found this explanation of data parallelism on SageMaker useful. I think it can be helpful to understand the underlying mechanisms. However, to make this all a little more concrete, let's take a look at how you would actually use the library. For this demo, I will show you how to use the library for your PyTorch neural network. There are minor differences in the instructions for PyTorch and TensorFlow, but I only have time to show one of them, and the details are all captured in the documentation. So here I am in SageMaker Studio. You can see that I'm running a Jupyter Notebook on a PyTorch 1.6 GPU-optimized kernel. In order to use the SageMaker distributed training library, you have to make some changes to your PyTorch code. I'll start the demo by showing you each change you need to make separately with as little surrounding code as possible. Then we'll look at a full PyTorch training script for the MNIST dataset with all of these changes included. To start, you need a neural network implemented with PyTorch version 1.6. In this case, I have a script with a simple neural network for classifying digits in the MNIST dataset. The first step to using the distributed training is quite straightforward. You need to import the SageMaker distributed training library and initialize a client. Since we're looking at data parallelism in this example, we import the distributed data parallel object. In the second step, you pin each GPU from your cluster to a parallel process. You do this by fetching the local rank of the GPU in the code. There are a few terms you need to understand here. The world size is the total number of GPUs available in your cluster. In this case, we have 2 instances with 4 GPUs each, so a world size of 8. Each instance has a rank, and each GPU on the instance has a local rank. The whole process can be done with just 2 lines of code, so it isn't too much work to add to your script. Next, you need to wrap your PyTorch model object in the SageMaker distributed data parallel object. Simply initialize the network you defined as you normally would, and then wrap it up in a DDP object in 1 line of code. Then you need to set some parameters in your data sampler. You can simply use the default PyTorch distributed sampler and have it generate 1 sample for each GPU in your cluster, aka your world size. These samples are just a collection of indices, which can be used in combination with a data loader to load the data onto the correct GPU. In order to do this, the sampler needs to know the world size and the rank of the instance, which you can set as attributes. In the next step, you just want to check your code for processes which only need to be completed by 1 node. Checkpointing is an example of this. There is no need for every GPU in your cluster to save checkpoint data. You only need 1 node, called the leader node, to take care of this. Testing the model on validation data after every epoch is another process which only needs to be done by 1 node. To achieve this in your code, simply use an if statement to check if the rank is 0. Place your checkpointing code there and do nothing if the rank is anything but 0. And those are all the changes you need to make in your script. The final step is to call the SageMaker training job with your training script and with data parallelism enabled. I'm going to assume that you're already familiar with SageMaker training jobs and how to pass your own PyTorch scripts and Docker containers to these instances. The argument we will focus on in this demo is an argument not often used, but which is required to enable data parallelism. Simply set the distribution argument to have this dictionary value, and you're good to go. Now let's look at these changes in a full script. First, I have a very simple model definition in PyTorch, where I define several layers and include the code for the forward pass. This should already look familiar to you. The train script is where we see the changes I've talked about. Below the PyTorch and other imports, we have the distributed training import, and we initialize the client. I have a train method, a test method, and a save model method, which are all pretty standard and no changes were made there. Then we get to the main method. We parse all of the arguments as usual, and you can see that we fetch the rank, local rank, and world size here. Next, we download the MNIST dataset from the PyTorch data collection, and now we create our sampler with the world size and rank arguments. After loading the train data on all instances, you can see that we only load the test data on the instance if it has rank 0, because we don't need every instance to run the tests. Finally, we wrap the model in the DDP object, and then we pin the instance to the parallel process. At the end of the script, you can see that we only save the model if the instance has rank 0. This full script is available on GitHub, so you can go through it in detail when you have some time. The link is in the resources section. Once we're happy with the script, we initialize a SageMaker PyTorch estimator with the distribution arguments set to use the data parallel library, and then we can go ahead and run the job. Now, after these explanations in the demo, I hope you feel comfortable with data parallelism and how to use the new SageMaker library to apply data parallelism to your own use case. There is a second type of parallelism, which we'll cover now, and that's model parallelism. So let's start by looking at why we need model parallelism. Generally, it is needed when your training jobs result in out-of-memory errors because your neural network is too large to fit on one GPU instance. This will happen more often as neural networks continue to grow in size like GPT-3. Fitting that onto one chip is a major challenge, so you need to split it up and store different parts on different chips. And that's called model parallelism. Even if your model does fit inside one GPU, it may be so big that there isn't enough memory left to store the data batch it needs to process. This is another situation where you may want to consider using model parallelism. Now, it probably won't be a surprise that there are many challenges with splitting up a model and running training across multiple GPUs. So there are a few things we recommend trying before you resort to model parallelism. Specifically, you should carefully consider if your neural network architecture needs to be as big as it is. Adjusting the hyperparameters in terms of reducing the number of nodes or the number of layers might still be sufficient to solve for your use case. You should also consider using mixed precision training, like switching from FP16 to FP8, if you can afford to lose a little precision. Another option is to reduce the batch size you use to train. Of course, this is only effective if the model itself fits on the GPU, and it can sometimes lead to a drop in accuracy. But we recommend experimenting with different batch sizes to see if this can solve the problem. And finally, consider reducing the size of your data records. If you are working in computer vision, consider reducing the resolution of your input images, or if you're working in natural language processing, try to reduce the sequence length of your input. If none of these techniques work and you still experience out-of-memory errors, then model parallelism is the final step. So how does model parallelism work? Again, let's look at a hypothetical SageMaker training job on a P3 8x large instance which has 4 GPUs. We have our dataset at the bottom from which the CPU pulls data batches to send to the GPUs. However, notice that each GPU houses only part of our neural network. The first GPU has the input layer and 1 hidden layer. The second and third GPU each have 2 hidden layers, and the fourth GPU has a hidden layer and the output layer. Now imagine running a data batch through this network. It is impossible to perform the calculations for the hidden layers stored on GPU 1 until the calculations on GPU 0 are finished, right? So how can we do parallel processing? Well, to be honest, model parallelism is not true parallelism. It is simply impossible to calculate layers later in the network until earlier layers have finished their calculations. The goal with model parallelism is not to speed up the training process, but to make it possible to train very large models. And a secondary goal is to maximize our use of the GPUs and have the process run as efficiently as possible. So when we talk about model parallelism, this is what we mean. When GPU 3 receives the calculations made by GPU 2 on the first batch of data, then GPU 2 is free to work on the next batch of data, while GPU 1 works on the third batch, and GPU 0 receives the fourth batch. This way, the whole system is processing multiple batches at each time, and using each GPU as efficiently as possible. And coordinating this system can be very challenging. With the SageMaker Model Parallelism Library, you don't have to worry about how to implement this yourself, because it takes care of all the logic for you. But let's look at a few details before we dive into the demo. The first challenge with model parallelism is deciding how to split your model across the different GPUs. As you can probably imagine, there are several different factors to take into account. Fortunately, the SageMaker library can perform automatic model partitioning. You can specify if it should focus on optimizing for speed or optimizing for memory, but you don't have to worry about much else. If you do want to partition your model yourself, then the library does offer the option for manual partitioning too. Now, as with data parallelism, the library supports PyTorch and TensorFlow. Since these frameworks structure their neural networks in different ways, the automatic partitioning varies slightly based on your framework of choice. On this slide, I'm showing an example of how it works with PyTorch. In PyTorch, you build your neural networks with the module base class, and a large neural network will typically consist of many smaller modules. During the training phase, the SageMaker library will run a tracing step over your code to generate a tree representation of your neural network. It will determine the execution time of each module, as well as the number of parameters used by the module and their activation. As you can see from the example on this slide, parameters can be shared by multiple modules as well. This tree structure is then used by the library to determine the optimal partitions. Each partition is assigned to an instance and consists of one or more modules. The library optimizes for computational load, measured through execution time, and memory use, determined by the number of parameters. When multiple modules share a parameter, these modules are placed on the same instance to avoid maintaining duplicate values for the shared parameter. By carefully balancing out these partitions, you avoid the situation where instances sit idle for a long time because a previous instance received a heavier load and is still finishing its computations. Once your model is partitioned and assigned to your cluster of instances, the next challenge is to determine in what order the computations should be executed. Remember that your GPUs can be processing different data batches at any given time, and our goal is to use the computational power of the GPUs as efficiently as possible. The SageMaker Model Parallelism Library gives you a choice between two pipeline execution schedules, simple and interleaved. With a simple pipeline execution schedule, the library prioritizes finishing the forward pass for each dataset before calculating the backward pass. In this diagram, the blue squares represent the forward passes, with the numbers representing the data batch. The yellow squares represent the backward passes. If we assume that GPU 1 contains the first half of the neural network, then we can see that each forward pass is calculated on that instance first. Only when it finishes calculations for a particular batch can GPU 0 start its calculations on that batch. As a result, GPU 1 will sit idle for a period of time while GPU 0 finishes up the last forward pass and starts calculations on the first backward pass. The second option is interleaved pipeline execution, where the backward pass is prioritized over the forward pass whenever possible. In this diagram, you can see that GPU 0 starts calculating the backward pass for data batch 0 as soon as both instances have completed the forward pass on it. This approach uses memory more efficiently because some memory can be released when the backward pass for a data batch is completed. In most cases, the interleaved approach also results in less idle time for your GPUs, so I recommend using this as your default. Now let's take a look at a demo for model parallelism. The structure of this demo will be very similar as the data parallelism demo. So here we are again in SageMaker Studio with a notebook that is similar to the last demo. I'll first show you the steps you need to take to adjust your PyTorch script, and then I'll show you a complete script as an example. Once again, you start off with a neural network built in PyTorch 1.6. In the first step, you import the SageMaker distributed training library and initialize the client. The code isn't exactly the same as in the previous demo, since we're now importing the model parallel component of the library, but the idea is the same. Next, you pin each GPU from your cluster to a parallel process. This is exactly the same code as used in the data parallel example, so let's skip over this step. Then you initialize your PyTorch model, optimizer, scaler, and scheduler. This time, you have to wrap both your model and your optimizer in SageMaker-specific objects. The code for this is quite simple. Just initialize your model and optimizer and wrap them in the objects from the SMP library. Notice that your scaler and scheduler can be left just as they are. The model parallel library needs to scan your code and build up the tree representation. To help accomplish this, you need to add decorators to your train and test step methods. It's just a matter of adding one line of code before the method definition, but it is very important. Next, you'll need to perform post-processing on the output of the computations going through the network. This is because the library splits your data batches into smaller micro-batches, which are fed to the pipeline one by one. The results have to be merged through post-processing. This is actually very simple to do because the output of your decorated train step method will be a SageMaker step output object. And this class provides several methods for post-processing. Just choose a suitable method and run this. And that's it for the changes you need to make inside your script. Next, we use a SageMaker PyTorch estimator to create the training job, again using the distribution argument to specify how the job should be run. Notice that there are more arguments you need to set in order to use model parallelism. For example, you can specify which pipeline execution schedule to use, or whether to optimize on speed or memory. You can also specify here if data parallelism should be used together with model parallelism. All of these arguments are documented, so I won't go over each one of them in this session. Let's take a look at the full script instead. Once again, I have a neural network defined with PyTorch modules. In this case, I have defined two smaller networks called Net1 and Net2, and then a parent module which combines the two. This shows how a large PyTorch network is likely to consist of multiple modules, even though this example is actually very simple. Now let's look at the most important components in the training code. At the top, we of course have our import statement. When we scroll down, you see that I have a train step with the correct SMP decorator. This train step only contains the code specific to training, so it's called within another train method, which takes care of moving the data to GPU before calling the train step, post-processing the results from the microbatches, and calling the optimizer. The same setup is used with the test step and a surrounding test method. Now let's look at the main method. Here we see that we initialize the SMP client. Then we pin the GPU to a parallel process, which is the same as with data parallelism. I'll skip over the data loading code, but I recommend looking at it in your own time to see how you can deal with both data parallelism and model parallelism used together. After the data loading steps, I initialize the model as well as the optimizer. And a little further down, I wrap the model and the optimizer in their respective SageMaker objects. As with data parallel processing, notice that we complete certain steps only if the instance is the leader node. In this case, the leader node will perform all the checkpointing. Here, it is checking if a checkpoint directory needs to be created, and here, it can load the model state from the existing checkpoints. You'll see this type of code limited to the leader node throughout the script. Finally, we can define our SageMaker training job, setting the various parameters to enable model parallelism, and then we can go ahead and train the model. So I hope you found those explanations and demos useful. It can be a lot of information to take in, so I recommend taking your time to read through the documentation and familiarize yourself with these new libraries. Before we close this session, I think it's worth taking a look at some of the results achieved with this new library. So here are some of the results when comparing the SageMaker Data Parallel Training Library with an implementation of Horovod, an open-source distribution training network. Remember that the SageMaker library has been implemented to specifically take advantage of the underlying EC2 instance topology. We see this reflected in the results, with improvements in both speed and scalability. For example, if we look at the second row, which shows the results for a faster RCNN model, then we see that using the SageMaker library results in a speedup of 80%, as well as a scaling efficiency improvement of 37%. For a BERT model, shown in the last row, there was a speedup of 44%. So these are some significant improvements. For model parallelism, the benefit is very straightforward. When training a MegaBERT model and a GPT-2 XL model without model parallelism, you encounter an out-of-memory error. With model parallelism, you're able to train these massive models through SageMaker. So hopefully, after listening to me talk about this for half an hour, you're interested in trying out these techniques for yourself. I've compiled a list of useful resources on this slide, which should help you get started. I should also mention that the SageMaker Distributed Training Library is available at no extra cost. You only pay for the compute resources you use to train your models. And it is available in every AWS region where SageMaker is available, so there should be nothing stopping you from giving this a go. If you enjoyed this session and you want to access more machine learning content from AWS, there are a few options after Summit. The training and certification team has over 65 free digital courses, as well as instructor-led training offers. You could also aim to get your AWS Machine Learning Specialty certification. And with that, I would like to thank you again for taking the time to listen to this session. I really hope my explanations will help you apply distributed training to your own machine learning projects. I just have one final request for you, and that's to fill in the session survey. It should only take a minute of your time, and it really helps me out to know what you thought of the session. I hope you enjoy the rest of AWS Summit.